Imagine if we could zoom through space so fast that we could reach a new galaxy in just 1 second. Sounds cool, right? But get this. Even if we could, it would still take us a mind-blowing 63,376 years to visit all the galaxies in the part of the universe we can see. And get this. Scientists think that what we see is just a tiny slice of the whole universe, like peeking through a keyhole. They figure that only about 5 out of every 100 parts of the universe are visible to us. Now, our own cozy corner of the cosmos, the Milky Way, is no slouch either. It's packed with 400 billion stars. And when you think about it, it takes light thousands of years to travel from one galaxy to another. That's how vast and spacious our universe is. Milky Way Galaxy. What's even more astonishing is that the universe is expanding in all directions at a speed faster than the speed of light. Famous physicist Brian Cox recently said that the universe is so vast that we can't even imagine it. This is the picture that Hubble took, and you see that it's anything but empty. It's called the Hubble Deep Field Image. It's one of the most important and fascinating images in the recent history of astronomy. It's not empty. It's got lots of structure, lots of points of light, and virtually every one of them, over 10,000 of them, are actually galaxies, distant galaxies. So they're not stars, they're galaxies. Now those galaxies on average have what? 100,000 million stars like our sun in them at least. So 100,000 million stars in each one of those 10,000 blobs. The most distant object in that image is 13.2 billion light years away. Now, light travels at 300,000 kilometers per second, 186,000 miles a second. And at that speed, it's taken over 13 billion years to travel from the most distant object in that image to Earth, to a Hubble Space Telescope. Now, when you think that the Earth is only just under 5 billion years old, it means that most of the light from most of the galaxies in that image began their journey to us before there was an Earth. And for some of the most distant galaxies there, they were over halfway here when the solar system was just a cloud of gas and dust. It hadn't yet coalesced into the sun and the planets and moons of the solar system. So, imagine what that looks like when you extend it over the entire sky. Well, this is a beautiful map of the observable universe. Brian Cox. So how big is our universe? Is it infinite, or does it have an edge? What is its ultimate fate? What existed before the Big Bang? And what lies beyond it? Let's dive in to find out. To begin, the fact that we can determine the observable universe's size to be 93 billion light-years across is truly astonishing. But how do we come up with this? The story starts with an Australian mathematician and physicist named Christian Doppler, who lived in the 19th century. Doppler was trying to explain a peculiar phenomenon related to electromagnetic waves. When an observer moves closer to the source of a wave, the length of that wave decreases, and if they move away, it increases. We now call this the Doppler Effect, and it applies to all types of waves. Doppler Effect. To understand this better, imagine you're standing on a sidewalk watching cars drive by. As each car approaches you, the sound of its engine appears higher in pitch. However, as the car moves away from you, the sound gradually becomes lower in pitch. This is the Doppler effect in action. For astronomers, the Doppler effect is crucial. By using stars as reference points, they can detect anomalies in the wavelengths they observe. If the wavelengths are increasing, it means the object is moving away, resulting in a redshift. Conversely, if the wavelengths are decreasing, it indicates the object is moving toward us, resulting in a blue shift. Fast forward to the 1920s when Edwin Hubble made a significant discovery. He observed that some objects in the universe were moving toward each other, while others were moving away. In a broader sense, it appeared that everything was moving away from everything else. Hubble's revelation was groundbreaking, shifting the prevailing view of a fixed and stable universe. What's more, this universal expansion seemed to be accelerating. Although we still don't fully understand why or how this expansion occurs, subsequent measurements have confirmed and refined this concept. Dark matter and dark energy are the leading explanations for these observations. Redshift. The study of redshift is fundamental for understanding cosmic distances, especially for objects that are incredibly far away. However, things become a bit tricky when dealing with vast cosmic distances. For example, if you're observing something 1 light-year away, you're essentially seeing it as it was 1 year ago. But during that year, the universe has expanded, increasing the distance 13.7 billion years. One of the most distant objects we've detected is a galaxy called GNZ11 or GNZ11, which is 13.4 billion years old, nearly as old as they come. However, despite the light from this galaxy reaching us from 13.4 billion years ago, it now lies much farther away than 13.4 billion light-years. In fact, astronomers believe it's a staggering 32 billion light-years from Earth. So it's essential to recognize that the universe's age in years doesn't directly correspond to its size in light-years. But we can go even further back in time. We can detect photons that existed before any stars or galaxies formed. These ancient photons originate from the cosmic microwave background, known as CMBR, a faint radiation filling all of cosmic microwave background radiation, CMBR, representing the earliest known electromagnetic radiation, stands as the oldest phenomenon we can detect. Understanding the cosmic microwave background radiation is greatly aided by the Wilkinson Microwave Anisotropy Probe, WMAP, providing precise information. WMAP, along with other estimates, indicates that the farthest observable photons we can detect originate from a staggering 46.5 billion light-years away, implying a minimum observable universe size of 93 billion light-years across. Earth's position within the universe remains imprecise, with no compelling reason to suggest a special or central location. The observable universe, estimated at about 93 billion light-years in size, raises the intriguing question of the universe's entirety. Is it infinite? We lack a definitive answer beyond the observable universe, making educated guesses based on various studies. For instance, one statistical estimate suggests the universe might be 251 times larger than the observable universe, equivalent to 343 billion light-years across. Another proposes a universe size of 10 circumflex, 122 megaparsecs. Expansion of the universe. The expanding universe, first observed by Hubble, reveals intriguing dynamics. Recent studies estimate an expansion rate of roughly 70 kilometers per megasecond. This expansion, expressed as speed per distance, indicates the universe's expansion is not objects actively moving away from each other, but rather the space between them increasing. Objects beyond 4,740 megaparsecs are receding from us faster than the speed of light, rendering them unreachable. Despite uncertainties, the expanding universe provides awe-inspiring insights into cosmic dynamics. Nature of the universe, finite or infinite. The debate over the universe's finite or infinite nature persists. If infinite, it poses profound questions regarding the existence of multiple variations and boundaries. Whether the universe will continue expanding indefinitely or halt and collapse remains uncertain. Theories regarding its ultimate fate include the Big Rip, Big Freeze, and Big Crunch scenarios, each presenting intriguing possibilities shaped by factors like dark energy and critical density. The universe's end, whether through expansion, heat death, or collapse, remains a topic of fascination and ongoing exploration in the realm of cosmology. Conformal cyclic cosmology. Conformal cyclic cosmology diverges from previous models, centering on the universe's closed geometry, akin to a spherical surface. In this framework, events like the Big Crunch resemble a singular breath, with the universe exhaling the Big Bang and inhaling the Big Crunch. This scenario could unfold through a reversal of the current expansion, possibly driven by dark energy. Parallel to this concept is the theory of the Big Bounce, suggesting a symmetrical cycle where the universe expands and contracts cyclically. Each iteration potentially mirrors previous occurrences, suggesting a recurring pattern across the universe's history. An emerging theory, the Big Slurp, tied to revelations about the Higgs boson, posits the universe's vacuum as inherently unstable. This instability could lead to catastrophic events, such as the sudden appearance of bubbles from alternate universes, threatening the annihilation of our universe. What existed before the Big Bang? Several theories attempt to tackle the enigma of what preceded the Big Bang. The multiverse theory proposes a vast cosmic landscape where our universe is but one among many, each potentially governed by different physical laws. This theory, however, raises questions about what lies beyond the multiverse. Another perspective, the cyclic universe theory, suggests that the universe undergoes endless cycles of expansion and contraction, with the Big Bang being just one phase. Quantum cosmology seeks to merge quantum mechanics with cosmology, suggesting that time itself might have originated with the Big Bang. Stephen Hawking's no-boundary proposal likens the universe to a closed surface without boundaries, making questions about a pre-Big Bang state meaningless.